Three companies, one mistake each. $100 billion gone. A lawsuit lost. A government report shredded in public. And the fix to all three of them lives inside only few words which very few folks actually understands. Vector embeddings, chunking, cosine similarity, and semantic search. Welcome back to AI Playground with Abhinav, and you are watching session 3 of Agentic AI series. Last session, we met three versions of the same employee. Employee 1, the LLM, brilliant but frozen in time, and wrong up to 1 in 4 times. And the bad part is, it never tells you when it is wrong. We also met with employee 2, LLM plus RAG, grounded, sourced, verifiable, and generating up to 88% positive ROI. We also met employee 3, LLM plus RAG plus Agentic AI, autonomous, self-directed, generating close to 171% average ROI. We watched that a gap destroyed real companies, Google, Air Canada, and Deloitte. And it was not because of a bad AI. It was because they all had a layer 1 AI, a brilliant reasoning engine with no live connections to verified and current information. And they deployed it in situations where the difference between a correct answer and a fabricated one had really bad consequences. If you missed that session, pause this video, go watch it first, please. Links is in the description. This session won't hit the same without watching that one first. Now, here is the thing about layer 2. The layer that took companies from confidently wrong to 88% ROI. We talked about RAG like it was a magic, but it's not. It's simply few concepts. And by the end of today, every single one of them is going to live in your head, not as a buzzword, but as a tool you actually understand. We are going to build our first production style AI assistant. Along the way, you'll finally understand why chunking matters, what chunk overlap does, what is vector embedding, how semantic search works, why embedding dimensions matter, and how actually AI finds the exact information hidden inside thousands of pages of data. By the end of this series, you will have built that assistant from scratch, live. And once you have built it once, you are never going to look at ChatGPT at or at any other AI product the same way again. You are going to see the architecture hidden underneath. So in the last session, we identified the problem, right? But how do we fix it? Not by replacing the model, not by retraining it every week at a cost of millions. You fix it by changing what the model sees before it answers. And that is all about RAG. And the elegance of it, once you see it how it works, is going to completely change how you think about AI architecture. Now, let me do a little more deep dive. So, what you see on the screen right now, RAG has two sides. Think of it as two separate pipelines altogether. Pipeline 1, if you look on the top, is getting the knowledge in. What you see inside this red dots. Second pipeline, which is pipeline 2, is how you get the answers out. And let's deep dive how it works. So if you talk about pipeline 1, it starts with your documents. If you look on the left side, PDFs, contracts, internal wikis, product documentation, regulatory guidelines, pricing sheets, support transcripts, and whatever you can think of, right? Whatever holds the knowledge your AI needs to reason from. And step 1 is chunking. Those documents get broken into small, manageable pieces, paragraphs, sections, specific clauses, and those are not arbitrary cuts. Intelligent splits that preserve meaning within each chunk. Step 2 is embedding. Each chunk get passed through an embedding model. The embedding model converts language into mathematics, specifically into a vector of 1536 numbers that represents not the just word in the chunk, but the meaning behind them. And we will deep dive into this concept very soon. Step 3 is storage. Those vectors that you generated in the previous step, they get stored into a vector database. Now, this is your organization's knowledge base, converted into a mathematical form that can be searched by meanings rather than words. And what do we mean by that? We'll also cover that very soon. The entire pipeline runs once when you set up the system. Every time you add a new document, it runs again for that document. The rest stays intact. Pipeline 2, as you see on the screen right now, is all about getting the answers out. It's all about retrieval. Now imagine a user asks a question. That question goes to the exact same embedding model, converts to the same mathematical language, which is nothing but the vectors, as your stored documents. Remember in the previous slide, we said that we are going to store all the documents in a vector database in a mathematical language, which is nothing but vectors. So when you ask a question, the question goes through the exact same embedding model, converts it to the same mathematical language. Now the search begins. And it's not a keyword search, not a tag match. It's a meaning search. The vector database finds the chunks whose mathematical representation is closest to the user's query. And this is the retrieval step. The chunk that matter, and only those chunks come back. Not the whole document, not a dump of everything loosely related. The specific paragraphs, the specific clauses, the specific data points that are most relevant to what was asked. Now let's go to the augmentation step. What you see on the screen right now is part of the exercise where we try to get the answers out, which is augment and generate. The user's question and the retrieved chunks are combined into a single precise prompt. That combined prompt goes to the LLM. And here is the critical difference from everything we have discussed previously. The model is no longer guessing from its training data. It is reasoning from your documents, from verified, current, controlled information that you choose, that you indexed and trusted. The response comes back grounded, traceable, auditable. Every claim tied to a source, every source, something your team can check. Now, to summarize this entire pipeline 1 and 2, step 1, you have to teach your stuff. Break your documents into small pieces, chunks. Turn each chunk into strings of numbers that captures its meaning, which is a vector. And store all those vectors in a vector database. That is step 1. Step 2, getting an answer of a question. First step within step 2 is turn the user's question into a vector the same way. Retrieve only the chunks whose vectors are closest in the meaning. And then augment the prompt, the user query, by handling the LLM question plus those retrieved chunks. So instead of AI guessing from what it memorized in training, it is reasoning from your own actual documents. And let me talk about an elegant truth. Have you ever wondered how ChatGPT can find the exact answer from thousands of pages of documents in just seconds? And here is something even crazier. The AI doesn't actually read documents the way humans do. Instead, it converts every sentence into thousands of numbers, stores them in a mathematical universe, and then searches that universe faster than Google can search keywords. It sounds impossible, right? Now, by the end of today's session, you will understand the 3 secret building blocks behind every modern RAG system. And trust me, once you understand these concepts, you will never look at AI search and RAG the same way. So let's dive in. We talked about employee 1, the LLM only, and its big challenge, a brilliant mind locked in a sealed room, frozen in time. We talked about RAG and how it turns that into employee 2, grounded with access to your recent data. But here is the obvious question. Why can't we just upload our documents straight into the LLM of your choice and ask it to answer directly? Why go through all this hassle of chunking, embedding, tokenizing, and whatnot? To understand that, let's understand what it actually takes for an LLM to answer a question. Because an LLM doesn't read words, like I said, it reads tokens. Now, what is a token? A token is roughly three quarters of a word, sometimes a whole word, sometimes just a fragment of one. For example, if I use the word refund, refund is one token. Unbelievable, as a word, it is closer to two tokens. Un plus believable. Every word, space, and punctuation mark in your prompt gets broken down into these pieces before the model ever processes a single one of them. So when someone says a model has 128,000 token context window, that's not 128,000 words. It is roughly 96,000 words, about close to 190 or 200 pages. Now, when you look at it, it sounds like a lot, right? That I have a capability or a context window to read up to 190 pages. Until you realize a single annual report, a terms and conditions document, or a product knowledge base can run into millions of tokens. You physically cannot fit the whole thing in. And in 2026, that ceiling looks very different depending on who built the model. So, what you look on the screen right now, GPT 5.5, 512,000 tokens, which is close to about 170 pages. Let's say 4 annual reports back to back. Cloud Opus 4.7, 1 million tokens, about 1,500 pages. And that's about the entire Lord of the Rings trilogy, which we can pass on in a single prompt. Gemini 3.1 Pro, again, like 1 million tokens, and that is equivalent to one mid-size company's entire code base, comments, everything. Grok 4.3, 1 million tokens standard, and then 2 million on the fast tier, which means that you can have every Harry Potter book combined almost twice. That can be sent as a prompt. And then there is Llama 4, the open source outlier. 10 million tokens, roughly 15,000 pages, your company's entire multi-year contract archive sitting inside one prompt. So, problem solved. Let's just grab the model with the biggest window and dump everything in it and then start asking questions, right? Sounds simple and plain, right? But not quite. Even if you could fit the whole thing in, the model's attention weakens further it gets from what it's currently processing. I'll try to explain this. Feed it a million tokens, and the fact buried in the middle get quietly lost. Accuracy can drop by as much as half once you cross roughly 100,000 tokens, no matter how big the Windows advertised size is. Let me take one example. Say you have a load of your company's entire 1500 page employee handbook into one prompt, full 1 million tokens, right? We are not doing any chunking, trimming, nothing. Now, out of those 1500 pages, what about the content on page 740 buried in the dead center? And in that dead center lies one sentence which says employees based in California are entitled to 12 weeks of paid parental leave. Now, out of those 1500 pages, page number 740, which is in the middle, it has this one sentence. Now you did the same thing. You uploaded the entire 1500 page of document, and then you are asking your LLM, how many weeks of paid parental leave do we offer? What do you think will be the answer? The fact isn't there. Technically, it's in context, and the model reads every token of it, same as everything else. But it answers with the number from page number 12 or maybe from page number 1400, the beginning or the end. Not because it didn't know, because of where the answer is actually lying. And you won't imagine, there is actually a benchmark for it, and researchers called it needle in a haystack. I'm sure all of you must have heard about needle in a haystack, and this is an actually term that researchers use. Bury one fact at different depth inside a long document and then ask the model to find it. Accuracy near the start, very high. Accuracy near the end, very high. Buried in the middle, it can fall off a cliff. You're not able to retrieve it. Now you get better, more accurate answers when the model sees a small, focused, relevant piece of text, not a wall of everything you have ever written. And which is exactly why a giant context window was never actually the fix. In summary, LLM read tokens, not words, and even a massive context window doesn't guarantee a good answer. Since attention weakens towards the middle of long document, and accuracy can drop by half past 100,000 tokens. A bigger context window was never the fix. It just made the haystack bigger. And I'm even not talking about the cost it incurs, when we go for a bigger context window. Now, instead of dumping the entire 1500 page haystack in and hoping the model finds the needle, you break the haystack into small focused pieces ahead of time. Then, when someone asks a question, you hand the model only the one piece that actually answers it, not the other 1499 pages. And that is chunking. And it's exactly the topic where we are headed next. Now, to understand the fix, let's understand the most underrated decision in your entire RAG architecture. And believe me, it's not the model you choose, it's not the embedding provider, not the vector database, it's how you cut your documents, how you chunk them. I know that sounds too simple to matter, right? Now bear with me, because this decision, chunking, is responsible for more RAG failures in production than any other single factor. And most people never think about it for more than maybe 30 seconds, and that's strange. Now, a quick callback. If you look onto the screen, you remember tokens from let's say a minute ago, roughly three quarters of a word. Chunking is where that stops being an abstract idea and becomes an engineering decision you actually make. Because chunk size, that number you are about to set, isn't measured in paragraphs. It isn't measured in pages. It's measured in characters, and underneath that, in tokens. You break your large documents into small, self contained, independently searchable pieces called chunks. Now, each chunk gets its own vector, and each vector can be individually retrieved, and only the relevant pieces get sent to the LLM. The code you are looking at on this slide does all of this in two lines. So, if you look at recursive character text splitter, with chunk size equals 1000 and chunk overlap equals 150. And this is just an example. Now, here is what that 1000 actually means. 1000 characters run through a tokenizer, that's roughly 250 tokens. A quarter of what we talked about a minute ago. So why so small? Why not chunk size equals 8000? Because of what happens the moment this chunk leaves the splitter. It goes straight to an embedding model, and that model doesn't hand you back a paragraph. It hands you back one vector, one single point in space built from every token you gave it. Feed it 250 focus tokens, all about your refund policy. You get one sharp vector pointing exactly at refund policy. And if you start feeding it 8000 tokens covering refunds, pricing, shipping, and maybe let's say company history, you will get one blurry vector, right? Which is smeared across four ideas at once, pointing at all of them, are little and none of them is going to be precise. That's the real reason why chunk size matters. It's a precision decision. Small, focused chunks make small, focused vectors. And focused vectors are what makes retrieval accurate. Now look at this example of, it's a stellar commerce example, a company. Look at the right side of this slide. You have one document, the stellar commerce knowledge base. 50 lines of company information. That document get passed to the text splitter, and this is just an example we are covering right now. The document gets passed to the text splitter and we get 5 chunks. Chunk 1, it's all about company overview, founding year, customer count, headquarters. Chunk 2 talks about subscription pricing, basic, professional, enterprise tiers. Chunk 3 talks about refund policy, 30-day window, international orders. Chunk 4 talks about shipping times, US, Europe, Asia Pacific, transit times and whatnot. Chunk 5 is all about payment methods, Visa, MasterCard, PayPal. Each one is self-contained and each one is roughly 250 tokens. And each one gets embedded separately, producing its own vectors. So just imagine these 5 chunks producing 5 vectors. And that's its own position in that 1536 dimensional space we talked about. And we'll talk about what this 1536 dimension space actually means. But for now, just imagine 5 chunks, 5 vectors. Now we are going to map that space properly in just few minutes. For now, hold on to this 5 chunks, 5 vectors, 5 distinct points, 5 distinct meanings. Now, when a user asks, what is your refund policy? The system does not have to search through the entire 50 lines or all the 5 chunks. It finds chunk 3 and only chunk 3 and sends that piece, that vector, the vector that was generated from chunk 3 along with the user prompt to the LLM. So that augmentation step, it picks the right chunk, it takes the prompt, sends it to the LLM. Nothing more, nothing less. And the answer, what do you think the answer will be? The answer is precise. And moreover, the cost is low. The response is fast. And that is the power of chunking done right. Now, if you look at the stat cards, the statistics, right, at the bottom, 10 chunks from a 50-line document, 1000 characters, which is about 250 tokens per chunk, roughly 1 paragraph, and about 10 seconds to index. Now, here is the open question I'm going to leave with you. What happens if a sentence, a critical sentence, falls exactly on the boundary between 2 chunks? Half the sentence, let's say, is in chunk 3 and half the sentence is in chunk 4. Now, when I'm vectorizing chunk 3, vector 3 is incomplete. When I'm vectorizing chunk 4, vector 4 is also incomplete. And neither chunk or neither vectors contain the complete thought. So when the chunks are vectorized, neither vector will fully represent it and neither vector will be able to give you the right answer. So when the system searches for that kind of sentence, it finds nothing. It again starts hallucinating. And that is not a hypothetical failure mode. That is exactly what happens when you set chunk overlap to 0. And that brings us to the next important concept called chunk overlap. Now to explain chunk overlap, let's take an example. Now user asks, what is the refund policy for international orders? Now the correct answer is sitting in the document somewhere. And the answer lies in the text which says, return any item within 30 days, full stop. International orders qualify for the same window. But the AI says, when you ask this question, LLM comes back and responds that I could not find this information about international orders in the provided context. Now the information was there, the AI missed it. Do you know why? Because the sentence was split in half between 2 chunks. half of the information was in first chunk, half of the information was in the other chunk, and the LLM could not relate or connect between those. Now this exactly is called the boundary problem. Let me explain one more thing. Look at the left side of this slide, the red card, the without overlap example. Chunk A ends with return any item within 30. Now chunk B starts with days, full stop, international, qualify, and then the remaining text. Now the entire sentence, which actually makes sense, return any item within 30 days, international orders qualify for the same window. That does not exist in either chunk. The complete sentence, the full sentence, which actually makes sense, doesn't exist in either chunk. So what happens when you create vectors out of those chunks? It will never be able to retrieve that information. It was split exactly at the worst possible place. Now, when the system searches for content about international order refunds, neither chunk gets a highly similarity score because neither chunk contains the complete thought. The answer is invisible. Now, this is the boundary problem. And it is not rare. Every time you chunk a document at arbitrary character positions, you're kind of gambling, or you're rolling a dice on whether important sentences end up splitting or they will be captured as a whole. So with no overlap, you lose that bit more often than what you expect. Now let's look at the fix, which is a chunk overlap. Now look at the green card at the bottom with overlap of, let's say, 150. Chunk A ends with within 30 days, and then there is an overlap section. Chunk B start with again that overlap section and then continues with the rest of the things, right? So if you look at within 30 days, it is there in chunk A. Within 30 days, it's there in chunk B. And look at the diagram on the right side of the slide. Chunk A, the block on the left contains the main text. The amber block on the right, that is the overlap. Those 150 characters get repeated. If you look at chunk B also, it starts with the same amber overlap text, then continues with the new content in purple. The amber text, the overlap, that is your insurance policy. It means that whatever query comes in, if the answer sits near a chunk boundary, at least one of the two adjacent chunks will contain the complete sentence, and the answer is never lost. The statistics card says 150 as an overlap characters. Now, rule of thumb, set an overlap to 15% of your chunk size. Now, if I take an example, suppose you choose 1000 characters chunks, then make 150 characters overlap. That is the default in this application, and it is a sensible starting point for most of the applications. You go below to 5% and you start losing boundary sentences. You will have more boundary problem. Go above 25% and you are wasting compute, repeating so much text that your index grows significantly without a proportional gain in the retrieval quality. 15%, I would say, that's a sweet spot. Now, with all this discussion, you know how documents get split and you know how boundaries get protected. Now, we have chunked, and the next step is to store these chunks. Now, imagine I ask you, how similar are these two phrases? First phrase is, the first string I would say is refund, and the second one is return policy. As humans, we instantly know that they are identical, right? Almost identical. But for a computer, they are completely different strings of text. And that's the first major problem AI had to solve. How can a machine understand meaning instead of matching words? So till now, what we are doing, in Google and every other search solutions that we have right now, we are looking for matching strings, matching words, right? Now, how can a machine understand meaning instead of matching words? The answer is vector embeddings. Every piece of text is transformed into a giant list of numbers, and in this case in particular, 1536 numbers to be precise. And here is the crazy part. No individual number means anything. The intelligence emerges from the pattern across all 1536 dimensions. Let's take an example. Think of it like a GPS coordinate, XYZ, right? Three coordinates can locate a place on Earth. Now just roll it up and imagine AI using 1536 coordinates to locate a meaning. And in a few more moments, I would show you how these numbers become the secret language of semantic search. Now here's the full mental model for this 1536 dimensional space. A dimension is just a number that measures one aspect of a meaning. Now you already live in a three dimension. Every point in the room is described by three numbers, X, Y, and Z, like I said, those coordinates. One dimension will not be able to locate anything in this room, right? A vector embedding does the same thing, but with this 1536 numbers or 1536 dimensions instead of three. And instead of a physical space, it describes a meaning space. So for GPS coordinates are used to find something in a physical space. 1536 dimensions are used to describe a meaning space. Each number in the vector sits between roughly -1 and +1. No single number maps to a clean human concept like this text is about refund and something of that sort. Instead, meaning emerges from the combination of all these dimensions. Now, this is why you cannot look at one dimension and understand it, right? Similar to the example I took, that you cannot use only one coordinate to locate something in this room. Now, the geometry is the key insight. When two chunks mean similar things, their 1536 number vector points in the same direction in that same high dimensional space, even if they are using different English words. So refund and return policy will produce vectors with a very tiny angle between them, giving them a cosine similarity score close to 1. Refund, and if you compare it with some other word, let's say API rate limits or something like that, will produce vectors pointing in a very different direction, giving a score maybe close to 0 or 0.1. Now look at the right side of the slide. 7 bands, and this is an example I have created just to explain that how these dimensions work. And this is just an example. Look at the first one. Dimension 0 to 200. Topic and subject. Now this is where refund, pricing, shipping, all these things live, right? This is the dimension range which answers that what is this topic all about, or what is this content all about. Dimensions 201 to 400, it captures sentiment and tone, whether it is formal versus casual, whether it is positive or negative, whether it is urgent or neutral. Two texts about the same topic can point to different directions here, can point to different sentiment and tones, and that gets captured between the dimension which is from 201 to 400. Similarly, 401 to 600, entity types. Now when we all know what entity is, right? What is it that we are talking about? We are talking about company names, dollar amounts, dates, right? That kind of stuff. Now 601 to 800, syntax and grammar. Is this a question or it's a statement? Is it a list or a clause? The structure of the language, not just the content. 801 to 1000, domain and context. This is the band that knows the difference between return in an e-commerce context versus return in a programming context. Same word, completely different meaning, different dimensions. So it talks about domain and context. 1001 to 1200, It talks about intent and question type. This is how a law, this is how, a how to question gets matched to a how to answer question, even when they share no identical words. And finally, the last dimension, I would say it's a fine grained nuance. This is where we may process your request and we will process your request. These are two different things, right? They produce a different vector. So the first one was we may process your request, and the second one says we will process your request. Subtle, but in legal and compliance context, it is critical. Now here is the thing. I want you to remember from this entire slide, no one designed these dimensions, and that's the key thing. No engineer sat down and said dimension 47 captures refund related content. No. The model learned all of this from training on hundreds of billions of words. And then the structure emerged. And that emergence is why it works. Now let's take an example before we get into vector embeddings. Suppose it's 11 p.m. A customer support representative is staring at a 3 open tabs and a 40-page knowledge base. A customer just asked about getting their money back. Now suppose I am that customer care agent, right? That customer support representative. And a customer is asking me about getting their money back. That means that I would in those 3 documents that I have as a standard operating procedure or SOP document as we call it, I would type refund policy into the search bar and I get 0 results. Frustrating, right? But I know the answer is right there. The document that I'm using, the 3 documents, the 3 tabs that I have opened, just happens to call it return policy. And what I was searching refund. One word different. Now, to a keyword search engine, I would say, in fact, that's the difference between finding the answer in 2 seconds and then never finding it. Because I am doing a keyword search right now. Now, here is what gets interesting. What if I told you AI can look at refund policy and return policy, 2 phrases that are not sharing those keywords, and they come back with a match and they tell you with a mathematical certainty that they mean almost exactly the same thing. Not kind of similar or not in the same ballpark. And the similarity score is 0.96 out of 1. That number is about to completely reframe how you think about AI search. And let me show you why. Remember from the last slide, every chunk of text becomes a vector, a list of 1536 numbers or dimensions pointing in a specific direction in a mathematical space. Now, here is the key insight that explains that customer representatives missed search. Similar meanings produce vectors that point in the same direction. And please note, I'm saying meanings. I'm not saying strings or keywords. Similar meanings produce vectors that point in the same direction. When 2 vectors point in the same direction, the angle between them is 0 degree. Just recall the trigonometry classes that you have done during your school times. The cosine of 0 is 1. Perfect match. When 2 vectors point in a different directions, suppose they are at an angle of 90 degree, the cosine of 90 is 0. No relationship at all. Now look at the formula on the slide right now, on the top right. Similarity equals cosine of theta, A dot P, divided by the magnitude of A times the magnitude of P. You don't need to memorize that. What you need to take away from this slide or this session is to remember this. Small angle equals high score equals similar meaning. And that's it. That's the entire concept. And it's the exact thing our customer representative keyword search had no way of knowing because it was doing word match or string match. Now let's go back to our scenario for a second. If the representative would have been searching with a vector similarity instead of keyword similarity, here is what the representative would have seen. Row 1, a refund policy versus return policy. And if you look at the screen right now on the left side, score is close to 0.96, which is nearly identical. Two different phases, but one meaning. Row 2, return any item within 30 days versus 30-day return value. Score is 0.89. Completely different sentence structures, different word order, still 89% similar because the meaning is the same. So are you looking at how effective and efficient this is? The vector similarity and this 1539 dimensions. Similarly, row 3, refund policy versus customer satisfaction, still a score of 0.61, not bad. Similarly, you can look at row 4 and row 5. Now, do you see the progression? 0.96, 0.89, 0.61, 0.28, 0.14 from near identical to near zero. And the magic is we never use the word refund in any of the chunks we compared against, not once. The model found the relationship through meanings, not matching words. And that's exactly the search our representative needed at 11 p.m. and exactly the one she didn't have. Now look at the two-dimension projection, which is there on the bottom right. Look at the diagram. Now this is just an attempt to flatten that, to compress that 1536 dimension space into something you can actually see. Think of it like this. Imagine a room full of objects floating in a 1536 dimensional space. It's impossible to picture, I understand. And just imagine you took a photograph of that room and you collapse all that depth into one flat 2D image. That photograph is what you are seeing on the bottom right. Now watch how the chunks cluster. The dots in the green, refund and return, shipping items, they cluster together in the logistics region because they are about similar things. The blue dots, pricing tier, transaction fees, they cluster in the pricing tier or pricing region. The amber dots, API rate limits, data and privacy, cluster in the tech region. Now here is the payoff. Our customer representative's question, what is the refund policy for international orders? That question becomes a vector 2 and it lands directly into the logistics cluster because that's where the answer actually lies. Now, if you are using ChromaDB or Pinecone or whichever vector database you're running or you're using, none of them searches for keywords. And they all do the same thing. They find the dots sitting closest to your question's marker. Refund and return policy share 0 character, but they scored 0.96 out of 1. Cosine similarity finds both. Keyword search finds neither, unless the exact word happens to match. Now, our representative, the customer representative, didn't need a better search bar. She needed a system that understands meaning and not the keywords. I'll take a pause. So now you understand how text becomes a vector and how vectors get compared. But here is the question our representative would actually ask if she knew all this. How did refund policy end up sitting in that exact spot in vector space in the first place? Because before any of this comparison magic can happen, your documents have to go through a process. They get split, they get overlapped, they get embedded, indexed, and they are made retrievable. And every single one of those decisions changes whether your AI finds the right answer or it misses it completely. The same way our rep did. The process is exactly where we are headed next. Cosine similarity. Now, this is a number in your rack config that is quietly responsible for the quality and the cost of every single answer your AI produces. Now, most people said it once, never, and they never look back at it and say that why did I set this number? They never touch it again, and they have no idea what it actually does. And that number is k. K equals 6. Now, by the end of this slide, I hope that you will know exactly why it's 6, why it's not 3, and why it's not 20, and why that one decision matters more than what most people think. So let's start with the search type parameter. Now, search underscore type, that equals similarity. This tells ChromaDB or your VectorDB, whatever you're using or you're running, that when a user asks a question, you search for chunks based on meanings, not keywords. We covered this in the last slide, right? We are searching based on meanings, not on the basis of keywords, not on the basis of metadata, or not even on the basis of recency, meaning. Now, quick recap. Since this is the engine behind everything we have built, every chunk becomes a vector. And a list of 1536 numbers. And the way we compare two vectors is cosine similarity, the angle between them. Small the angle, high will be the score. Similar will be the meanings. That hasn't changed. What's new here is what we do with those scores. We talked about getting 0.96 out of 1, right? That was a score. And how it works, the user, it types a question. That question passes to the same embedding model that indexed the chunks, the chunks when we created this vector and the vector database, right? And those were all 1536 dimensional numbers. Now, ChromaDB computes the cosine similarity between that question vector or the user query vector and every single chunk vector database. So you have your vector from the query, and then you have your vector database. Every chunk gets a score. If it is 0, completely unrelated. If it is 1, it has an identical meaning. And then the chunks are ranked, highest score to lowest. And here is the crucial part. You don't return all the chunks. You don't return top 50%. You return a specific number of chunks. That number is k. Now look at the formula on the slide. Similarity equals cosine theta equals a dot b divided by the magnitude of a times and the magnitude of b. That is pure geometry, no guesswork, not keyword magic. Just the angle between your question and every chunk in the database. I'll say it again. So that's the angle between your question, your query, and every chunk in the database. The k is equal to 3 versus k is equal to 6 versus k is equal to 20 decision. That's what we are going to talk now. Look at the three comparisons. K equals 3 means conservative, fast, cheap, but potentially incomplete. If the full answer spans across more than 3 chunks and you are setting k equals to 3, you will get a partial response or a miss. K equals 6, balanced, default, the one with a green badge and the check mark in the middle. K equals 20, you are saying that you are going to bring top 20. It's going to be expensive. It's going to be noisy. And we talked about it. If you are, it's like the same problem, right? You are giving so much context with so many topics that the topic you are trying to search gets buried down. So k equals 20 is expensive. It's noisy. It sends roughly 20,000 characters to the LLM, about 3 times the tokens, slower response, and a real risk of confusing the model with irrelevant context. Now, let me give you the actual numbers. K equals to 6 at 1000 character per chunk is close to 6000 characters of context. Now, 6000 characters of context is about 1500 tokens added to your prompt per query. Just remember that number, 1500 tokens added to your prompt per query. K equals to 20 at 1000 characters per chunk is 20,000 characters, which is about 5000 tokens. Three times, more than three times the cost, three times the noise, marginal gain in the answer quality. Now, the math strongly favors K equals to 6 for most enterprise use cases. But here is a nuance, the thing that separates good RAG engineers from great ones. Now, K cannot be a one size fits all, right? You cannot assume that K equals to 6 is always going to give you the best results, best quality. Now, here is a tip, when to adjust K. If you have long, complex documents, legal contracts, technical specifications, you might need K equals 8 or 10. The relevant information can genuinely be spread across more chains. As against to that, if you have simple factual queries, like let's say, what is the price of the professional enterprise plan? K equals 3 is probably fine, right? The answer lives in one chunk. Now, comparative queries. For example, compare the refund policy for a domestic and an international orders. You need at least K equals 6 because the answer requires pulling context from multiple places. Now start at K equals 6. Measure your retrieval quality and then adjust from there. Now look at the bottom of the slide. As retriever, search type equals similarity and then K set to 6. That one line in the entire retriever configuration for our RAG system, it configures everything. Two parameters, four words, bringing enormous impact. Search type equals similarity. It says find chunks by meaning using cosine similarity that we talked about and not by keyword match. K equals 6. Return the top 6 most semantically relevant chunks from your vector database. Those 6 chunks go directly into the LLM's context. The LLM never sees the other chunks in the database, never even knows that anything else exists. The quality of your AI's answer depends entirely on whether those 6 chunks contain the right information. Which is why chunk size matters, which is why overlap matters, which is why embedding model and the similarity metrics matter. It all feeds into this one retrieval moment. Now, let me leave you with the big picture. Across the last 5 slides or last 15 minutes, we have built a complete foundation of a production grade RAG system. First, we talked about how a text becomes a 1536 dimensional vector, 1536 numbers, encoding topic, sentiment, entity type, syntax, domain, intent, nuance, and whatnot. Now, they're encoding everything all at once. And the vectors are compared with cosine similarity. We took an example of refund policy and return policy. That gave us a score of cosine similarity score of 0.96. Keyword search would have scored 0. In our example, documents get chunked into 1000 character pieces, one paragraph, one idea, one independently searchable unit. Then we saw how adjacent chunks share 150 characters of overlap. So no sentence ever falls through the boundary gap, the boundary problem we discussed. Towards the end, we saw the retriever uses that same cosine similarity to score every chunk in your vector database and returns the top 6 chunks or top 6 vectors. Those 6 chunks and only those 6 are ever sent to the LLM. And that's the only thing LLM, knows about it. Now that is RAG. And that is why it works. That is why organizations implementing this properly are seeing hallucination rates drop to a near zero on a governed data. Now, every single ingredient for building a production grade RAG assistant, we have covered. And in the next session, we code, and you're going to be surprised how easy it is. Embeddings, chunking, retrieval, the math behind k equals to 6, you already know it now. Now what's left isn't learning, it's assembly. Taking every piece of this puzzle and snapping it into a working system. Now, if this session gave you even one real insight, hit that like button right now. Subscribe if you haven't already, because next session we go live, we build it, a complete RAG pipeline built from scratch, real code, real documents, in fact, your documents, real queries, and you walk away with a working system, not just notes. Drop a comment below. Tell me what surprised you most. Was it the 1536 dimensions, the boundary problem, or the k equals to 6 math? And send this to one person on your team who is making AI decisions right now. This is AI Playground. I'm Abhinav Rawat. Stay curious, stay disciplined, keep building. See you in the next session. Thank you.